In this video, I am explaining how to write covariance in terms of expectation of random variable. See, covariance is to measure the linear relationship between given two variables. It is used in bivariate distribution. See, for bivariate frequency distribution, covariance between two variables x and y is defined as covariance of x comma y equal to summation fi into xi minus x bar into yi minus y bar whole divided by summation of fi, where x bar is the mean of a first variable and y bar is the mean of a second variable. Therefore, in the same way, for bivariate probability distribution, so here it was a frequency distribution. Now, in the case of probability distribution, to define covariance between the two variables x and y, here x and y are two random variables, we need to get the relationship between those two random variables. So, in that case, we calculate the covariance as a summation over I pi into xi minus x bar into yi minus y bar. This is for discrete random variable. So in the case of continuous random variables, covariance is calculated using the integral from minus infinity to infinity. This is double integral from minus infinity to infinity x minus x bar into y minus y bar into f of x comma y into dy into dx, where f is a probability, joint probability density function. So this is the definition of covariance of a bivariate probability distribution. Now I have to write this covariance in terms of expectation. We have E of x is equal to summation of pi into xi in the discrete case, and in a continuous case it is minus infinity to infinity x into f of x into dx. So this is the definition of expectation. Now here in this case, xi is replaced by xi minus x bar. Therefore, in the definition it becomes x minus x bar into one more term is there as a product y minus y bar. So E of x minus x bar into y minus y bar as per the definition. This can be simplified as E of x minus x bar is nothing but mean of the random variable. We know that mean is nothing but expectation. So x bar is replaced as E of x. Similarly, y minus y bar is E of y, mean of the random variable y. So upon simplification, if you use the properties of expectation and simplify it further, you will get covariance as E of xy minus E of x into E of y. So this is the final formula which is in terms of expectation, where covariance is in terms of expectation. So covariance, the concept comes for bivariate distributions. In the case of bivariate frequency distribution, this is the formula. In the case of bivariate probability distribution, this gives you the covariance, that is giving linear relationship between the two variables. If the covariance is positive, means there is a positive relationship between those two variables, means one increases means other variable also increases. Negative covariance value means it is one increases other decreases. Zero covariance value, zero means then there is no correlation between those two variables. So in terms of expectation, covariance of bivariate probability distribution is given as E of xy minus E of x into E of y. Now if x and y are independent random variables, then in that case E of xy equal to E of x into E of y. You have seen what are independent random variables. So in terms of expectation, the independence of random variables is defined as E of xy equal to E of x into E of y. That is using the previous formula. See, here we got covariance of x comma y as E of xy minus E of x into E of y. If the variables are independent, then there is no relationship between those two variables. Hence, covariance becomes 0. Now the second property is v of x plus y. Variance of x plus y equal to v of x plus v of y. This is in the case when x and y are independent random variables. So this is the first result. All these results follow when x and y are independent random variables. So let us see how to prove this. V of x plus y equal to v of x plus v of y. See the second one, proof. V of x plus y. So let us write the definition of V of x, that is in terms of expectation. We know that V of x is equal to E of x minus E of x whole square. Second order central moment is the variance. Therefore, variance of x in terms of expectation is given by E of x minus E of x whole square. Use this definition here. So here in the place of x you have x plus y. So E of x plus y minus E of x plus y whole square. So this is equal to, let us simplify this, E of x plus y minus, use the property of expectation, E of x plus y is given as E of x plus E of y whole square. So this is equal to E of x plus y minus E of x minus E of y whole square. Taking this minus inside. So now this is equal to E of x minus E of x. I'll write these terms together. Ex minus E of x plus y minus E of y whole square. This is equal to E of, now let us use a plus b whole square formula. A square plus 2ab plus b square. So this is your a, this is your b. So x minus E of x whole square plus 2 into x minus E of x into y minus E of y plus y minus E of y whole square. I have used a plus b whole square formula. So this is equal to E of, now for this outside E, apply the property of expectation. That is E of x plus y is E of x plus E of y. Use it here. So this gives you x minus E of x square. Take this inside like this to second term, then to the third term, plus E of 2 into x minus E of x into y minus E of y. You can take 2 also outside, plus E of y minus E of y square. So this is nothing but definition of V of x. E of x minus E of x square is nothing but V of x plus, see what is this term? This is 2 times covariance of x comma y. So that we got it from the previous formula. See, here I got E of x minus E of x into y minus E of y. Finally, it is E of xy minus E of x into E of y, which is nothing but covariance of x comma y. Now here in the beginning it is given x and y are independent variables. So in the case of independent variables, covariance becomes 0. Therefore, this term vanishes. That I'll write in the next step. Plus, this is the definition of V of y. Variance of y. So as the covariance equal to 0, because x and y are independent random variables, therefore this is equal to v of x plus v of y. So for independent random variables, v of x plus y is equal to v of x plus v of y. In the same way, you can prove for independent random variables v of x minus y equal to v of x plus v of y. Remember, for v of x minus y, it is not minus here, it is again plus. So v of x minus y equal to v of x plus v of y. That means variance of x plus y is same as variance of x minus y. And the last one, v of x plus by equal to a square into v of x plus b square into v of y. You can prove it in the same way using the properties of variance. All these hold only in the case when x and y are independent random variables. Now see here one problem. If x and y are independent random variables with variances 2 and 3. So variance of x is equal to 2, variance of y equal to 3. You have to find the value of variance of 3x plus 4y is equal to how much? We have to make use of the fourth property which I have explained. So v of ax plus by equal to a square into v of x plus b square into v of y. So this is v of 3x plus 4y now, that is equal to 3 square into v of x plus 4 square into v of y, that is equal to 9 into v of x is 2 plus 16 into v of y is 9. So this is equal to 18 plus 48, that is equal to 66. Therefore, v of 3x plus 4y is value equal to 66. So this is how we write covariance in terms of expectation and properties of variance when x and y are independent variables.